Okay, so continuing with Lewis structures, and we're going to start talking about the shape of molecules in more detail. And to be honest, carbonate's one of those ones, if this is the one you're going to kind of try and memorize or maybe just work on more frequently, this is a classic example, okay, because it shows you many things. Shape, and we'll show you an example at the end of the packet as an old exam question for shape, and also what's called resonance forms, okay? So we're going to finish off the one we were working on, yeah? So we'll go through from the top, follow the rules explicitly, and see what we can come up with for a Lewis structure for the carbonate ion. So we got CO3, 2 minus. Rule 1, how many electrons? So carbon has 6 valence, oxygen, sorry, start again. Carbon has 4, column 4, 4 electrons. 3 oxygens, each has 6, that's where I got that 6 from, plus the 2 from the outside, right? Okay, so let me just kind of move that up so you can see it. All right. So, carbonate, 4 for the carbon, 3 oxygen, 6 each, 2, add that up, 24 electrons, right? So we've got 24 electrons to sprinkle around this framework, and it's got carbon, which ideally should look like that, a carbon with 4 sticks, oxygen, 2 sticks, 2 lone pairs. Now, because this is a molecular ion, we're going to play a few tricks, okay? We're going to kind of press this theory as far as it can go, and these won't look perfect at the end of the day, okay? That's why, you know, this is kind of a weird example, okay? But we do the best we can. Let's show you how that works. So, carbonate. Carbon obviously is going to go in the middle, and then there's 3 oxygens will surround it, okay? Fair enough. Follow the rules. Next, single bond inside to outside. Just following those rules we did for the previous examples, okay? And then complete the outer octets. Oxygen, of course, needs 8, 2 for the stick, and then 6 more. Just like we did with CO2, right? So very similar to what we've done before so far. Okay, then when we get to that point, we add up the electrons. 2, 4, 6, 8, same 8, same 8. So 3 to 24. It's got 24 electrons. Fantastic, right? But obviously it's not right, is it? Because carbon needs 4 sticks, it's got 3. Oh, not happy, right? Oxygen needs 2 sticks. Again, not happy, right? These little faces are optional. All right. So what do we do? Well, as we saw, when, for example, here, even though we've got the right number of electrons, we can get the valency right by turning owned pairs into shared pairs. There we go. Now look at this oxygen. Is it happy? 2 lone pairs, 2 sticks. Yes, perfect, right? Look at carbon now. 1, 2, 3, 4 sticks. Sure, 2 singles and a double, but 4 sticks, right? So this one and this one are fine. But these 2 are not, right? What we're going to do? Well, can we put these electrons in here? No, because that'll give carbon, if we did that, we'd have 1, 2, 3, 4, 5 bonds. Carbon can have a maximum of 4 bonds because, hey, 4 bonds, 8 electrons. So that's as best as we can do. So we put a box around it, and because there's those extra 2 electrons, we put 2 minus up there. And that's as far as the theory takes us, okay? However, we're not quite done. This is what we call resonance forms, okay? Now, if you think about it, did I have to put the double bond here? No, I didn't, okay? I can put it in different locations. So there's actually 3 answers to this. And on the test, and the one in the back of the book, we can write this, right? So I could have put the double bond here, single bond, and then all the electrons, right? Or here at the bottom. So there's 3 spots if I could have put that double bond to make this work, all right? And that's that. So this actually has 3 answers, and these are called, I'll write it on the side here, resonance forms, okay? So it's like 3 answers rather than just the one, because there's 3 possible locations for that double bond, okay? And if you do this on the test, and we can just peek ahead to the question, all the way at the back, it says, draw Lewis structures, including all resonance forms, right? So you'd have to draw all 3. So we're kind of halfway done the last answer right now, okay? But, you know, it does also talk about shape, which we'll get to in a minute. Now, That's as far as the theory can take us. Is that how nature is? Is there 3 molecules in nature? No, there's just one, right? And what's the best way to explain this? Well, none of these, if you look at it, are technically stable. None of them have the right valency for every single atom. You keep some of the people happy all the time, right? So the carbon and one of the oxygens will be happy and 2 oxygens unhappy all the time. Can you keep some of the people happy all the time, or can you keep all of them happy all the time, right? Well, there's a trick to that. Now, this is not how this molecule is in nature. You can't have 3 answers, yeah? It turns out that this is very much like a cartoon. Now, if you remember a cartoon, now back in the day, back in England, growing up in, dare I say, the 1970s, one of the most highlights of our month was when the phone book used to arrive, okay? Because you could have fun with the phone book, not like Bart Simpson fun, but actual cartoon fun, right? So you take the phone book, and on the bottom in the corner, you draw a little stick guy like that, right? On the next page in the corner, you draw a stick guy like that, right? And on the next page, you draw a stick guy like that. Next page, that. Next page, that. And then what would you do? You'd flick the corner and this would animate, right? So this is like a single cell for a cartoon animation, right? This is basically what these are. These are single cells in an animation. In real life, electrons move close to the speed of light. So this double bond is rotating around here so fast it's kind of blurred out, it's kind of smudged out. And what we see is like an average structure, okay? So if you looked at this, you would find all these bonds were the same length. That means they're the same strength. They have the average, which is 1 1/3, right? And that's what the structure actually looks like in real life. It's called a delocalized structure because it's not local to one bond, one pair, a bond, right? Delocalized. And that's what it looks like. So if you average these 3 resonance forms out, you get the delocalized form, right? And that's how nature really has it, yeah? But we can't model that with this theory. That's as best as we can do. So whenever you can have like a weird answer, and this will always be true, if you've got a weird structure that doesn't obey the rules of valency, so for example, not every oxygen is right in the structure, how do you make it work? You use resonance forms. It's kind of like juggling a hot potato, all right? So keep those hot potatoes in the air, you're fine, okay? So resonance forms give stability, okay? And we'll look at a few weird molecules later, okay? If the molecule doesn't look right to you, if the rules of valency aren't obeyed, if the number of sticks and paddles isn't right, sticks and lone pairs isn't right, resonance is the way to go. So it's one way to get around issues with the model. Okay, so we'll go on to that later with the CO2 example in more detail. But in order to get there, we have to do some theory with shape. Okay, so as we already mentioned, molecules have certain 3-dimensional shapes. Okay, now the theory that governs shape is called VSEPR, which is kind of a bit of a mouthful, and what it really stands for is V, valence, S, shell, electron pair repulsion theory, VESPR, VSEPR, valence shell electron pair repulsion theory, which is kind of a mouthful, right? But I don't even call it that because it's very, very simple. Turns out that if you want to figure out the shape of a molecule, all you have to figure out is how many clumps of electrons are around the center atom. So in each example, we've had a center atom. If we figure out how many clumps of electrons are around that center, we can figure out the molecule shape. So valence shell electron pair, well, that's just code for clumps, isn't it? Every electron runs in a pair because either they're lone pairs or bonded pairs, so they're 2 dots, paddles if you wish, or sticks, right, which is a shared pair. So valence shell, that's where they live, electron pairs, okay, so sticks and lone pairs, they're all negative, right? So they're clumps of negative charge, so they repel one another, okay? So if you maybe think about putting 2 North Pole magnets on the hands of a clock, right, they'd kind of like repel away, they'd rotate round to as far away from each other as they can get. That's kind of how the theory works. So things rotating around a common center the same charge will repel one another. So it's repulsion theory. I just call it the clumps theory. and we'll see how that works in a second. Okay, so the trick is, carry on as normal, draw your Lewis structure, and then we'll just look at the center atom and figure out how many clumps are around it, number of clumps, or as it says down here in our little kind of book example, electron domains. The number of clumps determines the three-dimensional shape. So first one, if I got 2 clumps, so this is in each case the yellow is the center atom. If I got 2 clumps around it, that might be carbon dioxide. That's an example in a second, we'll see. If I got 2 clumps around it, it's going to be a straight molecule. It's going to be linear. Okay, we'll talk about bond angle when we do the example. If I got 3 clumps, flat triangle, trigonal planar. If I got 4 clumps, like methane, tetrahedral. So, you know, in Chemistry 100, we only do up to 4 domains, yeah? Okay, but if you did like Chemistry 101, we go as far as 6. We get some more exotic shapes. But for now, 2 clumps around center, 3 clumps, and 4 clumps. What's the eventual shape of the molecule? All right, it all depends on this repulsive electron geometry, which we'll talk about. Okay, so let's dig in. I'll kind of keep that to the side for now, and we'll come back to it, okay, and fill in some stuff. Now, what we're going to do, we'll look at a few molecules. Some we're actually familiar with, because we've seen them already, okay? So, consider the electron pair bonded in lone pairs. Doesn't matter if it's a bond, a stick, or a lone pair. They're still a clump, right? So consider those bonds and lone pairs as clumps, which will repel, okay? Now, the best way to think about this is to think about one of my favorite films, and maybe you're familiar with this film, all right? Have you ever seen the film Gladiator? Okay, Gladiator is kind of an interesting film, all right? It's where, you know, they have, and if you look at my front page here, there's a picture from Gladiator, right? So, in the movie Gladiator, they, you know, have it in Roman times, and the Romans are a bloodthirsty lot, right? So they kind of execute people for fun in the Colosseum, right? So let's pretend we're in ancient Roman times, and it's time to kill a chemist, right? And this reminds me of the CO2 diagram, right? So imagine you have in your Roman Colosseum, and you know, they want to entertain us, right? So they have a pole in the ground, right? Which is like the carbon atom, that center atom, right? And then they have a ring, and then a rope, which is the bond, and then that's attached to a chemist, right? There we are, right? That's like oxygen, and that's like a double bond in CO2, isn't it? We've seen CO2 before. Then they bring in, just for your entertainment, another ring, another string, and something super dangerous, right? I'm not sure what this is, but it's super dangerous. Let's call it a crocodile, right? Okay, and then that's like another one. So if we look at it, right, we have a center atom, which is like a pole in the ground, and then we have these bonds, which are like ropes, which they can obviously rotate around, right? Now, if you think about it, let's pretend this is a chemist, right? And I'm reminded of the life of Brian here, right? Okay, so if this creature wants to eat me, so it's going to walk around this way, what am I going to do? I'm going to walk around that way, right? I'm going to stay as far away from the creature as possible. That's mutual repulsion. Why does that work in a molecule? Because I have 2 sticks, right? Now, remember, it's a clump, right? It's a double thick clump, but it's still a clump. Doesn't matter if it's a single line, double line, triple line, or even a lone pair, right? That's a clump of negative, and that's a clump of negative. They're going to repel one another as far away as they can around that center, right? So think of the hands of a clock, right? Repelling. It's always 2:45, right? Okay, so what's that angle? That angle is 180. So if I have 2 things rotating around the center, right, they will repel. Maximum bond angle is 180. Okay, so this angle between the crocodile and me is always going to be 180 if I want to stay alive, right? So that's like mutual repulsion. That's how that works, all right? So with 2 clumps, go back to the first page, that was the center atom. Pull it up so you can see it. That was the center atom, and then this is a clump. That's like a double bond, right? Okay, there just happen to be oxygens on the end, but it doesn't matter. It's all about the clumps repelling, and they rotate around that center. So 2 clumps, they're in a straight line, so it's said to be linear, and that's a 180-degree bond angle. Okay, bottom line is 2 clumps, linear. Okay, fair enough. And that might be, for example, CO2. So let's draw that on the side. CO2, that's 180 degrees because I got 2 clumps. All right, now let's pretend If I draw you a picture, here's the picture here, right? So here's the model from the kit. Now it's all about these clumps around the center. So even though these lone pairs are there, they're not involved in bonding to the center. So we can kind of ignore them just for clarity. If you look at that, you can see that the model kit has given us a center carbon and 2 oxygens either side. And when we did this, we said, oh, it's kind of common sense to put them either side in a symmetric way, because your brain was actually kind of predicting this behavior. Your brain says, okay, well, they got to spread out as far as possible, and that's how you do it with 2 things, okay? It wouldn't work if they were kind of at right angles to one another. They want to repel as far away as possible. So remember, these bonds are rotating around this center, and they go linear, right? Go linear. Okay, it just so happens that the atoms are on the end of the bonds, and the bonds are the things that are repelling one another because they're clumps of negative charge, right? Okay. Now, next one, and keep it familiar, right? So one we've already done is CH2O, right? Now let's give you the analogy again, right? So let's pretend I survived my encounter with the crocodile. Now the Romans are pissed, right? So, oh, we have to kill him. Okay, bring on another animal. In fact, bring on 2 animals. Okay. So here I am with my superior aerobic fitness, right? If you watch Life of Brian, that's funny, right? So what do? Oh, they bring out another crocodile. I'm terrible at drawing, I know. And they bring out another animal. Don't know what this is, but it's super dangerous. It's like a weird, I don't know. Okay, now, so we have 3 things, right? 3 ropes. Right? Let's pretend all of us got together backstage and said, hey guys, no stress, just keep as far away from each other as you can and we'll all survive this, okay? And that's exactly what's going to happen. So if you look at this, it looks like CH2O, all right? So carbon, 2 hydrogens and oxygens. When we did that one earlier, this is what we got, right? We can look back and look at that, yeah? If you put the extra dots on there, right? But the bottom line is this, there's 3 clumps. Again, doesn't matter, singles, doubles, triples, doesn't matter. What's around the center atom, okay? 3 clumps. So how far away are they going to be? What's that angle going to be? And that angle, that's all going to be the same angle. It's like an outside, it's like a triangle, right? So if I looked at it just with like a picture like this, from the top, all those angles are the same. It's 120, right? So 3 clumps around the center spread out to 120, and they're all on the ground, so it's like a flat triangle, all right? And that's what we got. So if we go back here, 3 clumps, this for example is CH2O, that angle is, in each case, 120. So 3 clumps, it's a flat triangle, trigonal planar, okay? I do have one somewhere. Here it is. Take the outside clumps off. So there it is from the top. It looks like a triangle. From the side, it's definitely flat, right? If I hold it up. So it looks kind of like flat from the side, right? So trigonal, triangle from the top, planar, flat from the side. Okay. So it's called methanal. Okay, so CH2O. All right. So 3 clumps, 120-degree bond angles, trigonal planar, flat triangle. Now finally, ran out of space a little bit, so I kind of do it in the corner over here. This is one we've seen before. Okay, so when I have 4 clumps, CH4, all right. Now, here's one we did earlier in the class, the last video or so. Methane looks like a tripod, doesn't it? Okay, it looks like a tripod. All right, so we have to break into 3 dimensions here, so the kind of the analogy doesn't work anymore. A nice way to think about this is carbon, up, side. So they're kind of what we call, if I put it like that, it's kind of hard to do it on the video. But there. These guys are what's called in plane. They're kind of flat in the same plane, right? Okay, there we go. This one is coming out towards us, right? So we do it like this. And that one's kind of going back away from us. So we do it like that. So that is a 3-dimensional, oh, should we see that? 3-dimensional tripod. Okay, it's 3-dimensional tripod. So 4 clumps, it's kind of like a tripod shape, right? Now if this was a 3-dimensional and we kind of join the dots up, it would look like a pyramid with a triangular bottom. Okay, a 3-dimensional shape with 4 sides is called a tetrahedron or tetrahedral structure, just shortened TD. Okay, so 4 clumps, looks like a tripod. Tetrahedral, CH4. Okay, so both in the same plane, coming out, going back. Okay, 4 clumps tetrahedral. Now that angle there, obviously, if we drew this in 2 dimensions, all right, flat on the page, it's just a right angle, isn't it? It's 90 degrees there. But that's not how it is in nature. It can get further away. If it breaks into 3 dimensions, that angle is actually 109.5, which is bigger than obviously 90. Okay, so that angle gets bigger if it's a 3-dimensional shape. So when we get to 4 clumps for the first time, we get into 3D. Okay, so that's our only kind of 3D shape. Both of these are kind of flat, sit on the surface. This is more of a, the last one's more of a tripod, right? Okay. So those are the 3 basic shapes. Linear, 2 clumps. Trigonal planar, flat triangle, 3 clumps, and then tetrahedral, 4 clumps. Okay. All well and good, right? So that's all you have to do, you think. Oh, it's so easy. I just count the clumps and I get the shape. Well, that's only true in the examples we've seen so far. Okay, remember I told you that, hey, it doesn't matter what the clump is, single bond, double bond, which we've seen now, right? But it can also be a lone pair. Okay, and to best show you the effects of lone pairs on what we call molecular shape versus electronic shape, let's take a look. Okay, so we're going to look at CH4, NH3, and H2O. Okay, if I just draw these things out, well, we just saw CH4. It's like that tripod, right? So you have C, hydrogen up, hydrogen in the same plane, hydrogen coming towards me, hydrogen going back in there. Fair enough, right? Now here's the thing. It's got 4 clumps, right? So the electronic shape, 4 clumps, is tetrahedral. Now in every single example so far, the electronic shape, which governs everything, the clumps, right? Where the clumps are determines how, well, really where they go, because they repel, right? Okay. It just so happened that every single example so far, the clumps have been bonds, single bonds or double bonds. So on the end of the clumps, there are atoms. So if you think about it, where my arm goes, my hand goes, right? So the definition of molecular shape is really joining the dots between the atoms, yeah? So because there's an atom on the end of each clump, the molecular shape, which is really what we've been calling shape, because it's been the same thing, is the same, right? So when there's an atom on the end of each clump, the molecular shape and the electronic shape is the same. The electronic shape determines everything because the clumps repel, right? If there happens to be an atom on the end of each clump, it's the same shape. That's not always true. Let's look at what we did before, ammonia, right? So NH3 has that paddle, has that lone pair, right? So if I kind of do it in the same kind of way, I'll do a paddle going up, in plane, coming out, going back, okay? Now be careful. Electronically, how many clumps are there? There's actually 4. There's 3 that are bonds, but remember, this paddle is still a clump, right? It's just not bonding to anything. It's just a pair of electrons not going anywhere. So there's still 4 clumps. Clumps determine the shape. So the electronic shape, 4 clumps, is tetrahedral. Oh, interesting. So ammonia and methanol both have 4 clumps. They both have a tetrahedral, if we look at it, arrangement of clumps, right? However, if I look at the molecular shape, if I join the dots between the atoms, I can't see this, right? I can't see that top clump because it's not stuck to an atom. I can only see the atoms. From the top, it looks like a triangle, right? So it's trigonal. But is it flat? No, it's like a kind of a raised up tent, right? If I get that to the camera nicely. Let me see, it's kind of hard to do. Oh, there we go. See that? So it's not, all the atoms aren't sitting flat on the same plane. They're not sitting flat on the floor. It's like it's raised up, right? Okay. So it looks like almost like a raised up triangle. It almost looks like a pyramid, and that's what we call it. We call it a trigonal pyramid. Okay. Not trigonal planar. If they're all flat on the ground, like we saw with CH2O on the last page, it would be trigonal planar. But this is not flat, because the bond angle is 109, not 120, right? Okay. All these have a bond angle of 109 because they're all going to be tetrahedral. All right. Last one, water. There it is, right? We saw that one before. Water actually has 2 lone pairs, but again, 4 clumps, right? 4 clumps again. All of these have 4 clumps. So oxygen in the middle, up, in plane, out, plane, back. I kind of set that up like I've shown you, right? So, nope, wrong way. There we go. In plane, out of plane, back. Okay. So 4 clumps, electronically, 4 clumps, tetrahedral. But if I ask for the real shape or the molecular shape, pull the wings off the butterfly here, I got 3 atoms. Are they in a straight line? No, we call that nonlinear. Unlike CO2, which was 2 clumps, which was a straight line, 180 degrees, this maintains that 109 degree tetrahedral angle because remember, those butterfly wings are still there, we just can't see them, right? So those clumps are all repelling, and 4 clumps repels 109 each time, right? So they all have electronic shape, tetrahedral, with 109 degree angles. Then these are the molecular shapes. If I just join the dots where the atoms are, still 109 degrees between all those angles because they were set from the electrons, right? But we have new shapes now. We have trigonal pyramid for plucking off one of the lone pairs and nonlinear for plucking off 2. Okay, that's a very popular example. Okay, you might see that on a test at some point. Okay, what is the shape? And when they say shape, they really mean molecular shape. Up until now, they've been the same thing, but now we see that subtle difference. Okay, pluck off those wings of the butterfly and you kind of get what's left. Okay. Now, here's a question of the week, and I'll just run through this with you, okay? If you want to pause and try this, it's kind of challenging. I normally get students to do this in larger groups, and we kind of have a group discussion in class. But let's just do it. So if you want to pause and try it, feel free. What we got to do is do the whole workup for ozone, right? Ozone is a really, really interesting molecule, all right? Okay, it exists for sure, but it shouldn't, okay? So what I want you to, here's a kind of a checklist. We're running out of time here. I'm going to kind of continue with this in the next video, okay? Ozone, you follow the rules and you'll get 2 answers. Hint, hint, it has 2 resonance forms. This molecule shouldn't exist, but it does, okay? Just follow the rules, you get 1 answer, and then you have an option, where do I put that double bond, okay? So the 2 answers. And then, just do the number of clumps thing, and get the shape, get the molecular shape. The electronic shape and the molecular shape will be different, okay? It's a very, very important difference. So it's actually a nice time. We've got like just literally a minute left before the timer goes off and the camera automatically shuts off. If you ever wondered why I always run under half an hour, because my camera doesn't run for more than half an hour and it's telling me I've got 45 seconds left. So we'll stop there. Okay, and when we come back, it'll be the last video of the packet. We'll run ozone. We'll see how it's got 2 resonance forms, and then we'll look at the molecular and electronic shape. Okay, see you in a little bit.